Okay, this screencast is on what is called an action potential. And an action potential, ladies and gentlemen, is the rapid changes in charge across a membrane. The last screencast talked about resting membrane potential. And that, of course, is when a neuron is not firing. Action potentials occur when neuron is firing. Firing means that impulse is moving. We're going to take a look at the animation first to get the idea of what is going on. Listen to this, listen to what's going on there. You got sodium with the red and potassium with the purple blue there. All right, let's listen.
When the cell membrane is at its resting membrane potential, the activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
Okay, did you get that? I hope you did. All right, so an action potential is the firing of neurons. So we're going to go to this picture. This is the one I'm referring to in both the directions for the diagram notebook, and we took a look at in the last one. Picture A represents a neuron or an axon in its resting membrane potential. Positive on the outside with reference to negative on the inside. And it's a sodium-potassium pump that keeps a resting membrane potential. There's a difference between that and a voltage-gated channel. All right, so an action potential begins with a stimulus. All right, so in response to some sort of signal initiated at a dendrite, sodium channels open within the membrane of the axon. As sodium ions are more concentrated outside the neuron, the opening of the sodium channels causes an influx, that's in, of sodium into the atom, into the neuron as depicted right here. Because really, when you depolarize it, you want to reverse the picture of what you're seeing here. You want to have it positive on the inside with reference to negative on the outside. So the influx of sodium causes the membrane potential to become more positive. And so while the resting membrane potential is negative 70, an action potential is actually positive 30 or to positive 60 inside the cell with reference to outside the cell. And as the impulse moves, which is what the diagram really shows you, B, C, and D shows you the movement of the impulse down. Okay, when an action potential has moved past a section of the neuron, that section of the neuron needs to be repolarized. And repolarization refers to the restoration of a membrane potential following depolarization. And you want to get it back to being negative. So basically, you want to get it back to looking like picture A, negative on the inside. How does that happen? Following the influx of sodium, potassium voltage-gated channels open within the membrane of the axon. And as there are more potassium concentrated inside the neuron, opening the potassium channels causes what they call a passive efflux, moving out of potassium out of the cell. So I'll use the word they use. The efflux of potassium then causes the membrane potential to return to a more negative internal differential, which means -70, +30, back to negative. So it moves down. You've got to depolarize, followed by repolarize. You can see picture D shows you another. So basically resting membrane right here, repolarizing, depolarizing the next section. There was one other term that they used here that I want to make sure you're aware of. At the end of the animation, they called it a refractory period. And what a refractory period refers to is the period of time following a nerve impulse passage, right here, before the neuron is able to fire again. So there's time. It has to get back to its resting membrane potential. In a normal resting state, sodium ions are predominantly outside and potassium are mainly inside. That's resting membrane maintained by the sodium-potassium pump. But following depolarization, that's sodium influx, and repolarization, okay, potassium efflux, it's reversed. So before the neuron can fire again, the resting potential must be restored as was we said before. So let's go to the notes. We'll read the notes off to you. And there's the, play it off of that. It went to different. All right. That's what an action potential is, a rapid change from a negative to positive, back to negative in response to a stimuli. Now remember, and this is inside the cell with reference to outside. All right, so let's get, sorry. Stimuli causes a membrane to become less negative, And what happens then? Once the membrane reaches what is called threshold potential, and that means increasing from -70 to -50, it triggers, notice I did these notes in shorthand, it triggers an action potential, which triggers depolarization. The sodium channels open, and that is a voltage-gated channel. Sodium ions enter the cell, making the inside of the cell positive with reference to the outside of the cell. And what is that? All right, so the action potential is anywhere from +30 to +60. All right, so that as the impulse begins to move down and moves further down the axon, that which was once is depolarized must repolarize. All right, it reaches peak potential, and when it reaches a peak potential, the voltage-gated channels for potassium open. Potassium begins to flow out of the cell, which triggers the closing of the sodium-gated channels, and is going to trigger repolarization, which is going to put the inside negative with reference to the outside positive. And that is a repolarization. Now, it becomes a little bit too, quote unquote, repolarized. So, because the potassium channels remain open, and it's actually going to lower the membrane potential past resting membrane to -90. That's called a hyperpolarization. It happens during the refractory period. So once it reaches that -90, that's the trigger for the potassium channels to close, and the sodium-potassium pump resumes to get the sodium ion distribution back together. And only after that is it in resting membrane potential, and then can a neuron fire off again.